Download this code from codegive.com, link in the description below. Maintaining C/ABI compatibility, a comprehensive tutorial. Application Binary Interface, ABI, compatibility is crucial when developing libraries or applications intended to be used by others or across different versions of your own code. For C, the ABI defines how functions are called, data structures are laid out in memory, and how the compiler interacts with the operating system. Breaking ABI compatibility means compiled code relying on your library will likely crash or malfunction when linked against a newer version. This tutorial provides a deep dive into maintaining C/ABI compatibility, focusing on practical strategies and illustrative examples. Understanding the C/ABI. The C/ABI isn't a single, universally defined standard. It varies subtly across operating systems, compilers, GCC, clang, msvc, and even compiler versions. Key aspects include calling conventions. This specifies how arguments are passed to functions, registers, stack, the order of argument passing, and how the return value is handled. Decl, stcall, fastcall are common examples on x86. Different conventions can lead to incompatible function calls. Data structures. The layout of structs, unions, and enums in memory is critical. Padding, insertion of extra bytes to align data on memory boundaries, is compiler dependent and can change across versions, leading to ABI breaks. Name mangling. Compilers transform function and variable names into mangled names to handle function overloading, namespaces, in C++, though relevant for C interoperability, and other language features. Incompatibilities in name mangling prevent linking. Function pointer types. The size and structure of function pointers must remain consistent across versions. Global variables. Changes to the size or location of global variables will affect other modules linked against the library. 2. Strategies for maintaining ABI compatibility. 1. Header files are your friend and enemy. Public header files, .h. These declare the interface your library exposes. Never change the structure of declared data types, structs, unions, enums, or the function signatures, return type, argument types, and number, in public headers unless you're prepared to break ABI. Even seemingly minor changes like adding a member to a struct can shift its memory layout. Private header files. Internal use private headers for internal data structures and function prototypes not intended for external use. These can be changed freely without impacting external code. Example 2. Versioning. Use semantic versioning, example major.minor.patch, to manage ABI changes. Major version bumps indicate ABI breaking changes. Minor version bumps signify new features without ABI changes. Patch versions are for bug fixes without altering the ABI. 3. Source compatibility versus binary compatibility. Source compatibility means code compiled with older headers will compile successfully with the new library. Binary compatibility means code linked against an older library will work correctly with the newer library. ABI compatibility refers to binary compatibility. 4. Careful use of typedef. Use typedef judiciously. While helpful for code readability, avoid using typedef for structs or unions unless necessary for preventing ABI changes. Consider using struct tags directly in public header files. 5. Avoid compiler-specific extensions. Rely on standard C features to maximize portability and minimize compiler-specific quirks that could lead to ABI inconsistencies across different compilers or compiler versions. 6. Compiler flags. *FPIC, position-independent code essential for creating shared libraries, .so on Linux, .dll on Windows, that can be loaded at different memory addresses. *wall, where, pedantic asterisk enable strict compiler warnings and treat warnings as errors. This helps catch potential ABI-related issues early. 7. Testing asterisk. Thoroughly test your library with different compilers, versions of those compilers, and on different target architectures to catch ABI incompatibilities as early as possible. Use automated testing whenever possible. Employ integration tests to verify binary compatibility with projects using your library. 3. Code example demonstrating a potential ABI break. Let's illustrate an ABI breaking change. Code compiled against version 1.0.0 will expect my struct to be 8 bytes long. When linked against version 2.0.0, the size will be 12 bytes, causing memory corruption and likely crashes. 4. Handling ABI breaking changes. When an ABI breaking change is unavoidable, example adding a crucial feature requiring a significant data structure alteration, introduce a new major version of your library. This clearly signals to users that they need to recompile their code against the new version, avoiding unexpected behaviors. Conclusion. Maintaining CABI compatibility is crucial for creating robust and reliable libraries. Careful planning, diligent use of header files, versioning strategies, and rigorous testing are essential to minimize ABI breaks and ensure the longevity and stability of your code. Always prioritize clarity and consistency in your API design to reduce the risk of ABI-related problems down the road. Remember to always refer to your compiler's documentation for specific details on its ABI behavior.